Well, good afternoon. This is 12:15 or maybe even a little bit later on Wednesday, the 22nd of August, 2018. This is supposed to be Calculus 3 class, and right now I'm the only one in the room, which is not what it should be the first week of class. Now, I knew that Muhammad said he wouldn't be here today. I know Daniel, or Dan, I can't remember how you go by, can't be here today. But the other two, Tyrell and Jeremy, should be here today, so I don't know where you are. I can't remember exactly where we left off last time. It seemed like it was on safety, but I don't want to talk to an empty room on safety, so I'm not going to pick up there. I'm going to pick up. The next thing I was going to do was ask you where you needed to begin the course. Now, I know that two students who were with me this summer, we ended right around 11.4 or so. And I don't know that you actually need to know the cross product that much. That's what I was going to ask you. If you felt like you did, we would pick up and do the cross product and do a few of the things there, what they call triple scalar product and things like that, and do lines and planes in space. We may need to come back and pick up some of those. I was going to ask you, the people who are here, where you wanted to start, okay? But since nobody's here, I don't know where you want to start, so I'm going to start where we're supposed to for this course, and that's in 11.6. That's surfaces in space, okay? It's in Chapter 11, Vectors and Geometry of Space, and 11.6 is surfaces in space. That's technically where this class begins. In the syllabus, it's called them quadric surfaces, and we'll be doing those. So let's start with the objectives here of 11.6. Now, if later y'all want to back up and do something else, we can. But 11.6, the objectives here, recognize and write equations of cylindrical surfaces. Those are quadric surfaces, by the way. Recognize and write the equations of quadric surfaces, which of course are quadric surfaces. And recognize and write the equations of surfaces of revolution. We may not spend as much time on that because that wasn't mentioned in the course description. So let's pick up and go where we are. Let's start with cylindrical surfaces. Now, first the name. I bet you when I say what's a cylinder, most of you are going to describe a tin can, basically. You know, a circular thing that has a top and a bottom and goes up a certain height, okay? That is a very limited kind of a cylinder, okay? That is a right circular cylinder of fixed height, okay? Your basic tin cans, okay? But before we get into that, I guess maybe we should go back and do a little review. And I think, at least the people in my class, I think we did hit spheres before. And the one definition of a sphere is this one. X minus x0 squared plus y minus y0 squared plus z minus z0 squared is r squared, okay? Now that's sort of your classic definition of a sphere whose center is at x0, y0, z0. I think I will change the color of my pen, so it doesn't hurt being red there. That's the center of the sphere, and the radius of the sphere is r, okay? Now that's sort of the classic definition of it. Now what makes that a sphere? The fact that the x, the y, and the z inside the parentheses or outside wherever all have the same coefficients. Okay, that's what makes it a sphere. A sphere. Now, that's one way to express a sphere. Let me show you another way to express that same sphere. Let's divide every term on both sides of the equation by r squared. Oops, I can't write, sorry. Okay, let's try that again. Okay, now what we have is x minus x0 squared over r squared plus y minus y0 squared over r squared plus z minus z0 squared over r squared is equal to 1. Now, you could change that just ever so slightly more to be x minus x0 over r squared plus y minus y0 over r squared plus z minus z0 over r squared. Thank you for being here. Never thought I'd say that to you. No, I'm sorry, I didn't say that. Is equal to 1. Yeah, you're it so far. Okay?
The only one.
Only one so far. Now, Dan Farmer is trying to do the course by remotely because he works in the day and he needed to get it. So he's just going to try to do it strictly through his screencast YouTube videos. And I knew Muhammad said he was going to had to be out today. I'm sorry. Yeah, Muhammad. Because the day was a religious holiday. Right. Okay, so let me pause a minute here. Maybe on the time slot.
Yeah, do your thing, take your time.
What's that one?
So do your thing, take your time. I'm on the one, so hey.
All right. Now, see, I saw Dan after class on Monday, and we talked things over. When he got off work, he came by here.
Okay.
I just marked Muhammad here and not Terrell. I got off. Okay. Now, before I got started on calculus today, I would have asked if anyone had been here, where did we leave off last time? I know we finished the syllabus. Did we finish the research paper?
Yeah, we went over the research paper.
Did we get started on safety?
No, we did not.
Not at all.
Not at all.
We didn't do anything on safety.
No, not at all.
Okay, so since I have an audience now, I'm going to pause in this. We'll come back to this in a minute, and let's talk about safety. Now, you've been in my classes before, so you ought to be able to give this presentation. But what 3 areas of safety do we have to do? Pick one.
Active shooter.
Okay, starting with the worst. Okay. Active shooter. Okay, that's certainly something we all, in fact, everyone should have in the back of his mind. It's a terrible thing to have to waste mind space on, but just thinking what you do if you hear it. Now let's start with reality here. If you hear a pop, pop, pop somewhere going on that sounds like it could be shooting to you, the odds are, unless it's really close, you're going to hear it better than I am. So you stop me and tell me it sounds like gunfire. Okay? So, and if that's the case, then what do we put in motion? What do we do first?
Turn the lights off.
Second?
Turn the lights off.
Okay, we certainly are going to do that, and that would be a good first step. Yeah, I think so. But something else that is pretty important to do.
Call loss and
Yes. Now, one of the students pointed out to me this morning that the Lost in State app, do you have that?
I do. Well, I had it.
Okay, you don't have it now, you don't think, or you're not sure?
No.
Now, on the Lost in State app, if you have that, right at the top of the screen, see, I don't have my cell phone in here. I have it down in the office. I like to go off when I'm teaching. So, but right at the top of the screen of that app is emergency numbers on both campuses. That gets you right to the duty officer who has that phone always on his or her belt everywhere one time they're on campus. So someone has that phone whenever the campus is open. Okay? So that's the first thing to do. Somebody turning off the light, someone dialing the Lost in State police. They probably hear it too. They may be in a different building and not hear it. Okay? Because we only have so many police and they have to cover the whole campus. So good idea. Be sure you do the Bastrop campus. Okay? If you're here. Okay. And then they will get in touch with professionals. If you don't have that number, if you don't have the app, can't get that number right away, 911 will get you there just as well. But then they'll call our campus police and say, why didn't they call me? You know, so try to call campus police, but if you can't, 911. Don't postpone it looking for a number. So it's not a bad idea. If you don't have the app, put that number on speed dial. Awesome. And if you don't know it, go down and ask the officer there, you know where the police station is down on the first floor? Yeah, go down and ask them, what's the emergency number that I can always reach somebody in case of, yeah, whatever. Okay, so number one will be calling. Now, next, and turning off the lights. You're absolutely right there. As soon as that phone call gets made to, everybody turn off their cell phones. Because you don't want buzzing, you don't want ringing, you don't want something happening when he's outside the door. Hey, there are people in there. Okay. So the next thing I'm going to do, and this is one real bad flaw of every building I've been in on this campus, for active shooter type situations, which we really should be and have to keep in mind, every door ought to have some sort of a device here that you can lock from the inside. Right. And I don't know a single one that does. Okay? Because guess what? I can't lock it from inside. I can't just open the door and press a button. There aren't any buttons. I have to physically go outside, and I happen to have a key for this door, and I have to lock it from the outside. Don't you pull the door on me. No, you wouldn't think of doing that, would you? Okay. No, and then I'll come back in and pull it too, because I got a key. I can get back in this. No. Okay. So come back in. So I got this one. What's the problem with this picture? There's another entrance. This door, that door, that door. Okay. If that was the case, we didn't like him to come to the front back. Okay. I can't lock that door. So I would close the door, turn off the light, this way. Now, I can lock this door, but I don't want to. Because if I lock this door, it's still being from the outside. Now, we can't get out and he can get in. Right. Now, I can't lock this one because it requires a key, and I'll have a key for this one. Okay. But the good news is that's a good solid door, so I'm going to ultimately do something with it. This door, however, can't do the one in the hall, but I can lock this one. Now it's locked from the outside, not from the inside. Yeah. So I would lock this door for sure. Close that, turn on the light, get all the suits from here, and then I close the door lock. Bad news is glass. Okay. You can shoot right through it, bust through it, whatever, reach in and open the door. You may not know that, but you can. Right. So what I'm going to do after I lock this is close this door. Right. So he can't see there's anything on it. Now, even though I can't lock it, I may call on you to come and help me. I just thought of this last night, actually. And get this table and pull it over here and jam it here. So he can't come in. Now, if that's not long enough, we'll get the other table to put against it. We're going to make it as hard as possible for him to get here. Okay? Okay? And then I'm going to go and close this door so it doesn't lock. So we can use another lock door. Try to dissuade him as much as possible. Okay? Now, we've got the lights off, dial down 1-1. You've got that door locked. That's the not the hall door, but the next door locked. That one closed. This one closed. And where do we go? Behind the wall. So he can't see in and see anybody here. Lights off. Doesn't hear a thing. All the cell phones are off. No one's talking. And we're quiet as possible. He can look in here. Can't see us. He can even shoot through here. Can't hit us. Okay? He can even maybe shoot through the wood. Can't hit us. This might be even easier, but maybe not. I don't know. That's metal. But yeah, he's going to have a harder time. Okay? So we've made it as hard as possible for him. But I don't think he's going to waste some time on the bullets. He's looking for someone to shoot. He thinks it proves it. That's the key. That. If it were the case that it was actually happening, though, don't be a hero. You're young. You have your whole life ahead. I'm old. Most of mine's back there. Okay? So if anything does happen, I'll be the one doing it in front. Y'all get safe. Get behind the desk. Do whatever it takes. Okay? where, but hopefully it will never come to that. So there's active shooter. We stay over here until we get official word that it's all clear. Okay, we're not going to just any voice we have. If it's someone officially at the college, probably the police, they have keys, they would open it up and check. All right, so there's one safety issue, active shooter. Hopefully it'll never happen here. I hope
Right. I hope not.
I
hope not.
hope not. What's another?
Fire.
Fire. Now that could happen. Hopefully it won't happen here either. But let's start with the worst case scenario of a fire. That it starts in this room. For instance, my computer blows up. Okay? I don't think that can even happen, but let's imagine it did. And it starts some of the papers on fire and the book on fire. Oh no, not my book. Okay. So what do we do?
Fire extinguisher.
Okay. One thing we will want to do is fire extinguisher. That helps put out the fire here. But if we're not successful, everybody else burns up.
Call somebody.
Okay, actually that's a very good thing. And who would be the best person to call? Campus police. Okay, if you have that number, that. If you don't have the number, 911.
Right.
Okay? Okay, so that lets them know. But how about the rest of the people in the building?
Fire alarm.
Fire alarm. Where's the closest fire alarm to this room?
Down the hall. Like nowhere.
Okay.
That's all.
Nowhere on the second floor here is there a single fire alarm. This part of the building was built before that was on part of code. So what you have to do is go out of the door here, hang a left, go down the half flight of stairs, and then go past the restroom to that crossover corridor there that goes to financial services. That's on the first floor. That's why it doesn't show up here. But that's the newest part of the building. It's been built since I've been here. Okay? And when you go through those double doors, gray double doors, right across from the financial services, there's a fire alarm to the left or to the right. Those are the closest one, easiest one to do. Now, in a bigger class, I would say go in pairs. Because in case somebody trips and falls or something, the other one can still make it through there. Right now, it's just you and me. Okay, so we might actually, why not? Yeah, really. Actually, your idea though about fire extinguishers is the next to best thing. Where is the closest fire extinguisher? Just outside the room here, yes. Go out of the door, and when you hang a left, you bump into the fire extinguisher. About 5 feet from where I'm standing right there. I mean, you can't get much closer. I know all your life you wanted to break that back.
Right.
Yeah. Okay. So if you want to do that on your way up to the fire alarm, okay? No, actually, you should go on the fire alarm first. And now break the glass. Okay. So, but anyway, we do the fire extinguisher, but we make sure the rest of the building hears about it and the police know about it. And I'll try to put out the fire. If I can't do it, and even if I can, I'm going to grab my roll book and we're going to head out. Where do we go? Well, not right outside, but you're on the right way. We go out of the door, hang a left, go down the half flight of stairs, and immediately hang a left at the bottom, go down one more flight of stairs, and then head out of the building to your right. Go away from the building, perpendicular to the building, until you get at least 75 feet from the building. And that would put you in a nice shady, grassy area somewhere out there. That'd be a nice place to stay. That's not where they want us to stay. They want us to actually head, and here's the diagram. We're in this corner classroom right up here. And when we go out this exit here, you go down to the parking lot. And stay together as a group. Don't say, hey, building's on fire, no more classes, I'm out of here. Do not say that. Please, do not say it. The reason is that I'm taking the roll sheet. Now, I'm going to be the last one out. Remember, maybe it's a class tomorrow, one of my students had surgery over the break, and he has a knee and a big brace, you know. So he's probably going to be the last one out. I'm going to be the last one with him. So I'll always be last. Make sure everybody gets there. And I'm taking the roll sheet. When we get down there, I call roll. If anyone's missing, someone decided to take off and go home or go visit a friend or something like that, then we don't know where you are. I or somebody else has to go back into a burning building and look for it. So don't do that to anybody, even to me. Okay. So, that's what we do. We stay together as a group. Well, no, you can mingle some and stuff, but stay on campus until we find out what they want us to do. Because then they may call roll again and be afraid someone else got there. So we'll listen to what they say. All right, so that not just fire, but chemical spill, noxious fumes, whatever. Okay. Next, what's the third safety issue?
Tornadoes.
Yes, tornadoes or other weather conditions. Something from outside the building that is a hazard to us. So if you hear the alarm go off, and you may hear it before I will, but it's a pretty good alarm. I probably should hear it too. Okay, what do we do?
Go to the bathroom for safety.
Okay, here's what you think anytime those alarms go off. Wherever you are, whatever building, wherever you are, you want to go low and interior. Low and interior. So the restroom's on the first floor, not a bad place to be. Okay, so what we do, we go out the door here, hang a left, go down the little half flight of stairs, hang a left there, all the way down, and rather than going out, you go in. Do not go out. Oh my, the dog's outside, I need to go get him in. No, you don't. Okay, the dog will take care of itself. You need to take care of yourself. The road is the worst place to be in severe weather. Any kind of severe weather. So stay off the roads. Go low and interior. So we go down that flight of stairs, go interior, and you're right across from the restrooms. The lowest part of the building. Now, those restrooms are not a bad place to be. Because interior, walls are close together, lots of corners. And that's the greatest strength of the building. The corners and the walls, especially the interior walls. And that's exactly what you got here. Now, think about this building. You go down to that lower level, you're still second floor of this building, right? But you go through that corridor, and where are you? The first floor. You didn't go down a single step when you're on the first floor. There's no floor beneath that, and that's why they don't show it here, because that's first floor. This is second floor diagram. Okay? That means that beneath that is soil and foundations. Sturdy, solid stuff. So therefore, this wall back here, down onto the ground floor, all you got behind it is soil. Okay? It can't go anywhere. Okay? It's not going to collapse, because everything else, if it collapses up here, it stays there. Because it can't go any lower. It can't push any more of those walls down. Okay? So, that back wall especially is a really good place to be. The corners are great, but it just made me think, I don't want to spend 2 hours in the bathroom, You could or not, it doesn't matter. So, actually, there's 2 more steps to go down on the first floor. And then there's a little office there underneath this corridor. It's the academic dean's office. Now, the bad news is she's not usually on this campus very much. She was here the first days of this week, but I bet you she's on Birmingham campus today. She'll be most of the time. Every now and then she's over here. And then also every now and then some other person under her, like the associate dean or someone else, might be using her office. So if anyone's in that office, that's a good safe place to be because it's close walls, lots of corners, and they have that back wall here against very solid material. Okay? Now, if you can't get in there, don't break in or anything. Go on to the next room here is room 160, which is developmental math. I don't know if you know that one. Now, the bad news here is a big open space. You don't want to be in the middle of a big open space. Bad to be in a corner is the best, and the wall's the next best, especially if it's that back wall. That's a great place to be, or the side walls, or even the front wall, as long as the window's here. But that's okay. Okay, and there's plenty of room in there. Then you go through the glass doors in the hallway there. First room on the right has the glass doors. Is that computer lab? Smaller room, meaning closer walls, more strength, and 4 corners. So that's not bad, especially that back wall. Right. Okay. Now the next room to that is what I call the reference room. That has the atlases and those kinds of things in it. And that's not a bad room to be in. It does have that back wall, which is really solid and secure, but it also has lots of bookshelves. to be okay with you. But don't go any further in the library. Because any further you go, you're on an exterior wall. You don't want to be there. Anywhere there's a window, things can come flying through a window. And there you go. Tornadoes can send things flying in. They can send cars falling. You remember the movie Twister?
Yeah.
Okay, cows flying. Yeah, anything can be sent flying. You don't want to be in harm's way. So we go down that. Now, I did mention probably the number one choice of spaces to be. There are advantages to the ones I said, but actually the hallway is not too bad either. The walls are relatively close together. They're interior, so it's straight. Bad news is no corners. Okay. But here's the big advantage of the hallways. The odds are, if you have severe weather outside, you lose power inside. And if you're low in the interior, you're in the dark. No windows. You're not in a room with windows. That's what you're trying to avoid. So you're in the dark. The restrooms, the dean's office, the classroom, the computer lab, the reference room, none of those have emergency light. They're interior, low, dark rooms. The hallway does have emergency light on both ends. So, unless you're just going to try to grab a nap, then, and you just want to be able to see your friends when you're talking with them or whatever, probably the hallway is the choice. And usually you can sit along the hall and chat or whatever, stand, whatever, lean, whatever. But if you don't mind being in the dark, and say, good time for a nap, it sounds like to me, you can go to one of those other rooms. The restroom probably isn't the best place to be on the floor, but never mind. Okay. But let's see. All right. And we go down there, I carry the roll sheet, we stay together, I call the roll, make sure no one's missing. If you have wandered off somewhere, thought you could beat the storm home, don't try it, okay? But we're not going to know where you are. Someone has to come back upstairs in these rooms with lots of glass and things flying around and risk their life or health. So don't do that. Any questions then on safety? Okay, good deal. All right. Hopefully that covers that. Now, the next question I was going to ask, I did ask it, no one was here to hear it. Where do you want to start this term? I know for the summer we got, I think, through 11.3, which is dot products. I believe we finished that section.
11.3 did.
Okay, and we would have gone on to 11.4. Now, 11.4 is something you will run into in physics, but it's not really, I mean, there's some calculus involved, but it's not that deeply involved with calculus. You can add some calculus to it, but basically it's vector stuff. Do you want to do cross products?
Yeah, that's fine.
You do want to do that, okay? And 11.5 is lines and planes. You want to do that too? Again, there's no real calculus in here. Later we'll be applying calculus to this, but we can certainly do it if you want to. What's that?
We can do cross product.
Okay. And then lines and planes? Okay. And then we'll be where we normally would start, which would be 11.6, which is quadrant surfaces. So let me end what I was talking about before. We'll probably come back and do this later. Let me discard this and end this and go back to 11.4. We'll try to do this pretty quickly because, like I said, it's not really all that much calculus. It's mostly geometry, vectors, that kind of stuff. But it's stuff we'll use later if we get that far, and we'll be doing some cross products and stuff. So it's not a bad idea to know it beforehand. Otherwise, we have to pick it up later. So odds are we're going to review it later anyway. But let's do, okay. Chapter 11 is vectors and geometry of space, and 11.4 is the cross product of two vectors in space. Okay? Any questions before we get started? Okay. Now, the one thing I didn't have a chance to go over because I don't have it finished is my locator card, but you know how to read those. That will be out there on Blackboard when I get a chance to put them out there. Okay, so the objectives in 11.4 are find the cross product of two vectors in space. We may go back and review what in the world the dot products were, but we'll talk about cross products. And then we'll use what they call the triple scalar product of three vectors in space. And that does have some applications, okay? So let's start with the cross product, okay? Many applications in physics, big time, engineering, big time, geometry, pretty much big time, involve finding a vector in space that is orthogonal to two other vectors that you ought not know about, okay? For instance, if you know, and this is something don't know if you've run into before, I think we have, but if not, we will run into it. Anytime you have two vectors, any two vectors, they define a plane. Any two vectors are going to define some plane. Okay? Now, if you have that plane then, quite often you want to know what is perpendicular to that plane. The normal to the plane. That means orthogonal. Perpendicular, orthogonal, normal. Those all mean basically the same thing. So if you have a vector in space that's orthogonal to two given vectors, you have the vector that is normal to the plane defined by those two vectors. Okay? So that's what's important. Now, the only place that doesn't work if the two vectors are collinear, because any other vector is orthogonal to that. But as long as they're not collinear, then you can find the vector orthogonal to those two. Okay? So in this section, we'll study a product that will yield such a orthogonal vector, perpendicular vector, normal vector. It's called the cross product. Okay? It's most conveniently defined and calculated using the standard unit vector form. And we'll see that. Now, let's go back, a flashback to the summer, okay? What was the other product that we talked about? There's actually two others. When you're dealing with vectors, what three products do we have? So let's say we have a vector. Let me get my pen back. A vector V, that's everybody's favorite vector. A scalar product, meaning you just multiply a scalar by that and you produce a new vector. It's just either longer if C is large, shorter if C is small, or in the opposite direction if C is negative, right? That's just a scalar product. You multiply a scalar by a vector, you got a vector in the same direction or the opposite direction, depending on the sign of C, but that just makes a different vector going in some direction, shorter, longer, or backwards, or whatever. That's a scalar product. Okay, what's the second kind? That's the last thing we did in the summer. I mentioned it already today. Okay, we're talking about multiplying. Multiplying a constant times a vector, that's a scalar product. Now, back when we were multiplying, back in the grammar school age, what did we use for multiplying? A time sign, okay, a cross, right? When did we get sort of out of using the cross for multiplying? When you got into algebra. And why algebra? Because in algebra you picked up variables. And what's everybody's favorite variable? X. Well, you couldn't use a cross for multiplication because that's your variable of choice. So what did we start using? We either wrote the scalar number right next to the variable, just like we did the vectors, CX, AX, 7X, you just did it like that. Or you put them in parentheses. Or what was the other way you expressed the multiplication? The dot. Exactly. Okay? So in math, we could say X times Y. That means multiply. Well, in vectors, vector V dotted with vector U, okay, that is one type of multiplying of vectors. Now it's a dot product. Remind me of a couple characteristics of dot products.
Maybe like the L.
The what?
The L.
Okay, well, yeah, it probably has some of that in it. They always do. But what I'm talking about, if you multiply with a dot product two vectors, guess what your answer is? Say again?
When we say if you
multiply two vectors with a dot product, what do you get as an answer?
A variable.
A what?
A variable.
No, you get a scalar.
Scalar.
A dot product always produces a number, not a vector. Think of this. Force is a vector. It has a direction to it. I push on the chair with a given force. It takes off and moves. That means the displacement is a vector. What is the product of my force times that displacement? Have you had any physics yet?
Not yet.
Oh, not yet.
Okay.
Okay. Well, if you haven't hit it yet, you're going to find out that's called work. Force times the work is a scalar quantity.
Right.
There's no direction associated with work. You either do it or you don't do it. Okay? In energy, there's no direction involved. So when you do a dot product of two vectors, you get a scalar result. Okay? Now, when you do the other that we did back in grammar school, the cross U, guess what that gives us? We already said it. You get a vector that is perpendicular to the U of V. So a cross product produces a vector, a dot product produces a scalar. Okay? So they are not the same thing. So that little dot and the cross we used back in mathematics, they meant the same thing. They both meant multiply. They don't mean the same thing in vector. A dot product is a scalar number, and a cross product always produces a vector quantity. Now, ever done any mechanicking or other things like that?
Not yet.
Okay. Well, no, I meant in real life, you know. There is a type of wrench called a torque wrench. Have you ever heard of that?
Yes.
Okay, you probably heard of torque with an engine, you know, have a torque. Okay. Guess what? A torque wrench multiplies the force that you're applying on the wrench times the distance of how far you are from the thing you're applying. Have you ever heard of people talking about a cheater bar? No, okay. Let's say you had a bolt that you couldn't get off with your wrench, okay? Well, then put a pipe on the end of that, and now you've got more leverage, and sometimes you can break it, okay? Uh-huh.
Yeah. I've seen it before.
You've seen that, okay. What you're doing, you're taking advantage of torque then, okay? Torque is force that you're applying. You apply the same force if you're pushing here or if you're pushing out here. But now you have a greater distance, so you have more torque. Because torque is force times the displacement. Just like pushing the chair. Except pushing the chair, when you multiply force times displacement, you get a scalar quantity work. Torque produces a vector quantity because it's what they call a twisting force, which is a vector. Okay? And that's why your engine, have you ever noticed when the hood's up, someone revs the engine acts like it's trying to come out of there. It is trying to come out. The torque is pulling it. If you didn't have those motor mounts in there, and they're sort of flexible, they're leather or rubber or something like that, they're holding it in. If one of those breaks, it does go flying out of the engine. Well, you don't want that. Okay. So, and guess what? In the English system, work is measured in, force is measured in pounds, and distance is measured in feet, and work is measured in foot-pounds. Foot-pounds of work. But when you're using a torque wrench, it's force, but you see that force is in this direction, the displacement is in that direction. With work, the force is in this direction, the displacement in that direction. If they're in the same direction, that produces a scalar quantity work in foot-pounds. But when you're torquing something, your force is this way, your displacement is that way, they're perpendicular to each other, or at angles to each other. That produces a vector which is perpendicular to both of those. And that's your torque. Same units, foot-pounds. If you had a torque wrench, you'll see foot-pounds on it most of the time. It could be Newton meters, but that's the SI unit. But in the U.S. customary is foot-pounds. Same unit as work. Work's a scalar quantity. Torque is a vector quantity. Okay. That was a lot of blah, 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 right? So that's engineering talk. Okay. The study of a product yields a vector is called a cross product. And you use the cross rather than the dot. Clever the way they named it, right? And it's most conveniently defined and calculated using standard unit vector formula. I already said that. Because the cross product yields a vector, sometimes it's called a vector product. Well, if you extended that back to dot products, since it yields a scalar, then do you say you call that a scalar product? Well, no, that's what you call a scalar product. But don't confuse the name. But actually, in the old days, they call it a scalar product. The dot product was a scalar product. But what do you call that then? Yeah, that's a multiplication of a scalar product. But yeah. Well, that's a scalar product, so don't get those confused. Okay, so here is our definition of the cross product of two vectors in space. Now, these are going to be three-dimensional vectors. That's why they say space. Let's have vector U. Remember, bold means vector. I can't write bold, so I'll put an arrow over it. Okay? So just get you. That's U1, that's the component of U in the I direction, the X direction, plus U2, that's the component of U in the Y direction, that's the times J, which is in that direction. Now these are, remember what did we call these three vectors, I, J, and K? Yeah, we just had the name a little earlier. They're unit vectors. So most of the time when I write them, since I can't write bold, I don't put an arrow over them. I put an arrow over U. I put a little cap on them. Indicates it's a unit vector. Okay. And I, J, and K are called the standard unit vectors because they're always perpendicular to each other. Okay, this is the X direction, Y direction, Z direction. Okay? And those are perpendicular to each other. So the U is the component of, U2 is the component of U in the Y direction. Okay, so that's why we put it with the J. And U3 is the component in the K direction or the Z direction. Okay? And that's your unit, that's your vector U. Your vector V is then V1I. One means in the X direction. V2J plus V3K. Okay. Now, those are two vectors in space going out wherever they're going. Okay. Now, they don't need to be perpendicular to each other. They're just not collinear. Okay. These are two vectors in space. The cross product of their vectors is of the other vector, and we're going to do U cross V. Now, guess what? Back when we did scalar products, C times U, this is C times U. You could say U times C. It didn't matter. That was commutative. You could multiply the number times the whatever. Okay. When you do that dot products, it didn't matter what order you put those. But with cross products, the order matters. And here's the reason. Let's say these are our two vectors. Perpendicular, that would be a vector up here, but also the vector down here. And those are opposite each other. They're collinear with each other, but they're in opposite directions. So that's why the cross product, you need to be careful. And where do they get these strange products here? I'll show you and you'll say, oh, that makes a lot of sense. That's easy. Looking at this, they think, what is the rhyme and reason of that? Okay? The only thing that makes a little bit of sense is that the I, which is the subscript 1, neither one of those have a 1. And the subscript for this was 2. Neither one of those have a 2. And this one, the subscript is 3 up here, but neither one of those is a 3. So that's one thing you notice. And then, but yeah, which one do you put first? Yeah, that's difficult. okay? Until I show you a trick. It is important to note that this definition applies only to three-dimensional vectors. If you have two-dimensional vectors, you've got another issue, okay? If you have four-dimensional vectors, whoa, what's that, okay? We don't have four space. Well, talk to Isaac Newton. He talked about space-time continuum. Is it time? And then you talk with anyone in linear algebra, and they can have n space, you know, any number of components. So we have to figure out some way to get that far easier than trying to memorize, okay? So let me show you how to do that. If you're doing the cross product of two vectors, now have you ever heard of a determinant before? No. Okay, let me tell you what a determinant is. Okay? Usually with a determinant, you're talking about a matrix. You know what I mean by matrix? Maybe or maybe not.
A little bit.
A little bit. Okay. What a matrix is, one definition, a pretty standard one, a rectangular array of numbers. Okay, what do we mean by that? Give me some numbers, just random numbers.
1, 3, 5,
6. What? 8. Huh? 10. Okay, that is a good matrix. We call that a 2 by 3 matrix. 2 rows, 3 columns. Okay? If you hadn't given me a 10, I couldn't make much of a matrix out of that. It's not rectangular. That's rectangular. Okay? Now, it could have been 1, 3, 5, 6, 8, 10. That would be a matrix. It's rectangular. That would be a 3 by 2 matrix. Okay? Now, both of these are strictly rectangular. You cannot take the determinant of a rectangular matrix. Okay? You cannot. You have to only take determinants of square matrices, which is a special kind of rectangle. Same number of rows as you have columns. Okay? So, these can't do a determinant. So, let's start with a simpler one. 1, 3, 6, 8, say. Okay? Now, usually a matrix we put in braces like this. Okay? Not braces, brackets like this. You can take the determinant of that. Now, 2 by 2 is really easy to do. And you probably have almost thought of it in a different way, but the determinant of this matrix, the DET, determinant of that matrix, would be the product of the main diagonal, 1 times 8, minus the product of the opposite diagonal, which would be 3 times 6. So that would be 8 minus 18 equal negative 10. Okay? You've just taken a matrix, an array of number, and come up with a scalar value. That's the determinant of a 2 by 2 matrix. You can only take the determinants of square matrices. Now, we're more interested in the 3 by 3 matrix. So let's scratch a lot of this. Okay. In fact, all of that. And part of this. And we'll go and get rid of all of that. Okay. And let's make that a 3 by 3. Give me 3 other numbers.
2, 4,
6. Okay. We'll see if that works. Okay. Now, if you're trying to take the determinant of this, and by the way, the symbol for a determinant is a vertical line. It looks like you're taking the absolute value of a matrix, okay? But that's not what you're doing. But it's sort of similar. The only difference is absolute values can never be negative, and we just saw that determinant, and the first thing we did was could be negative. That's fine, no problem. But you're getting a value out of it. You have an array of numbers, and you're getting a single value out of it. Here's how you do that. Now, there's some rules, and let me tell you the rules. Okay? And I don't want to mess you up with all the nomenclature. let me just say this. Every position in this vector has a sign associated with it, either plus or minus. And here's what you do. It's really easy to do. Always start in the upper left, and that's positive. Plus, minus, plus, minus, plus, minus, plus, minus, plus. Or plus, minus, plus, minus, plus, minus, plus, minus, plus. Or plus, minus, plus, minus, plus, minus, plus, minus, plus. They always come out the same. As long as you only go horizontal or vertical, don't ever go diagonal. That's not the way to go. And they're always, this is always positive, that's always negative. No matter how you count them off, they do. In fact, the main diagonal are all plus values. Okay, and then every other one is the minus. So
That's how you tell which one.
okay, yeah. That's just get that concept down. In doing a determinant, every place has a sign, plus or minus. Okay. So here's what we do. We take you can start anywhere you want to, but let's start here. Let's start with the 1, and that's a positive value. So the determinant of that is going to be 1 times the determinant of what's left over when you eliminate the first row and first column. Everything that has a 1 in it. So that's 1 times 8, 10, the determinant of 8, 10, 4, 6. Okay? So we've done the first one. Now, you didn't have to choose the upper left. You could have chosen any value you wanted to. I would say one of the external values. Since we chose that one, I don't know what I just erased, but okay. What I'm going to do is erase that. Okay, now, next thing I'm going to say, you choose where you want to go from there. You could either go, since you chose this to begin with, you didn't have to. You could have chosen that, or this, or this, or this, or any on the external. Usually, first row or first column. Choose one there. We chose that. So now you can either use the first row or the first column. Which you want to use?
First row.
Okay, first row. Okay, good. So we use the 1. We're going to go here. What is the sign for that position? Negative. So we do a -3 times the determinant that we have when we cross out the first row and the second column, where the 3 is. And then you have the determinant formed by 6, 10, 2, 6. Right? Okay? Now, since we are going down the first row, you chose that. Okay? Then we have to go next to the 5. Okay? Because you did the 1, the 3, then the 5. And what sign is that one? Positive, plus, minus, plus. Okay? Plus 5 times the determinant of, wipe out the first row, first row, third column, and then you do the determinant left over by 6, 8, 2, 4. Okay? Now you have 2 by 2s, and those are easy, right? This would be 48 minus 40. Remember? Main diagonal minus the product of the main diagonal minus the product of the other diagonal. On the main diagonal. So that'd be 1 times 48 minus 40, that'd be 1 times 8. 8. Minus 3 times 36 minus 20. That would be 16. So minus 3 times 16 is 48. So this is 8 minus 48 is minus 40. And then plus 5 times 24 minus 16. 24 minus 16 is 8. 5 times 8 is 40. What do we have? Whatever it was. Add them together, that's your determinant of the matrix. Okay? Sort of see how we did that?
Yeah.
Okay. Now, all we're really interested in is 3 by 3s. Okay? Because we're in 3 space. Right. Okay. So here's how we use that concept of a determinant to take to find the cross product of a matrix. Seems bizarre, but it really does work. Okay? So I'm going to erase all that, but I hope you got the concept down. Now, okay, got it. This drives me nuts. Okay, we got it back. So let's say the cross product of U cross V. Okay? Now remember, U is U1I plus U2J plus U3K. And V is V1I plus V2J plus V3K. Right? So how are we going to do that cross product? We're going to say U cross V is going to be the determinant of, now here's a little problem. This determinant is not going to be just a pure number, because the first row is always I, J, K. They're actually vectors. The second row is whatever the first vector mentioned, and its I component was U1, U2, U3, right? And the third row is the second vector's components, V1, V2, V3. Now these are just numbers. They're scalar numbers. They're not vectors themselves, but I, J, K are vectors, and they're the unit vectors. Okay? Well, this time we're going to do just like you did, and we're going to pick to start with the I, and then we're going to do the determinant of what's left over. Well, what's left over is U2 V3 minus V2 U3. And that's multiplied by the unit vector I. Right? Okay. Then we're going to go to the J's. Okay? And we go to the J's. Okay? We're going to wipe out the first, the J column and the J row, and it's going to be take the cross product here. But what is J's position? Negative. So we're going to put a minus here and do the cross product or the determinant of this 2 by 2, U1 V3 minus V1 U3, or you could do it U3 V1, it doesn't matter, times J. Okay? And then we'll do the same thing for the K. Okay? And that's going to be, oops, I didn't erase enough, did I? Okay. With the K, we're going to wipe out the third column and do the vector left. And what's the position of K? Positive. So that's going to be plus, and do the determinant here, U1 V2 minus V1 U2. And that's times K. Okay, what do we have? We have U2 V3, and they reverse these, it doesn't matter, those are just numbers, minus U3 V2, doesn't matter which order you write these, because you're just scaling, times I, minus U1 V3 minus, and then they reverse these two, it's okay, either way, U3 V1, J, plus U1 V2 minus U2 V1, K. And guess what you got? You've got a vector, I, J, K component. And what's not obvious to you is this vector happens to be perpendicular to both U and V. You can't see that looking at this, but indeed it is. Now it's also perpendicular according to what we call the right-hand rule. So since you named U first, you point your fingers of your right hand in the direction of U, and then wherever V is, bend them in that direction, and where your thumb sticks up, that's going to be the K direction. That's going to be the direction of the problem. Okay? So point in the direction of V, cross to U, there's your cross product there. Point U, cross V, is pointing that way. So it can be pointing oriented any way you want to. U, cross V, up this way.
You said that was called the right hand rule?
It's called the right hand rule. We use the right hand for it. If you do left hand, you always get it backwards. Okay? It's called the right hand rule. They use that a lot in a lot of things. Okay. Now, there's an easier way to do this. Okay? And I'm going to show it to you right now. At least calculationally, it's easier. This gives you exactly that. Let's not use that. Okay? Let's start with the same thing we started with before. So let me erase some of this. I'm even going to you got it written down what the answer was, right? And it's right up here too. So, okay. Now, here's an easier way to do a 3 by 3. It doesn't work on any other size matrix than a 3 by 3. Okay? But here's what we do with a 3 by 3. Oops, I erased the K part. Okay. Repeat the first two columns. I, U1, V1, and J, U2, V2. Just repeat them. Okay? Now here's what we do. Okay? You add the downward diagonals. This will be U2, V3, I, plus, because you're adding them, U3, V1, J, I just like to put the vector at the end. That's the only reason I'm doing that. Plus, because you're going downward again, U1, V2, K. Then, and I'm going to erase my lines just so they don't get so confusing looking, we do your up diagonals. Because they're going up, those are negative. Okay? So that's going to be minus V1 U2 K minus V2 U3 I minus V3 U1 J. That is a J. Sometimes my eyes look like J, so that's a J. Now combine like vectors, okay? So these two go together. That would be U2 V3 minus V2 U3 I, okay? Combine your J's together, plus U3 V1 minus V3 U1 J, and then combine your K's together, U1 V2 minus V1 U2 K. Okay, now let's see how those compare. U2 V3 minus V2 U3, same thing. Okay, I. Now, this has the U3 V1 minus this, but you have the minus in front of it, and that flips them, and that makes it positive. So you got the same thing there. And then these are already positive. I forgot to put my plus sign here. Shame on me, and you let me get away with it. Okay. Okay. And that would be U1 V2 minus V1 U2 V1. So that's that. That to me is easier because otherwise I forget about minus into J. Okay? You do it this way, always your down diagonals are positive, your up diagonals are negative. That's why you put the other two there so you don't have to worry about, all that mess. Okay. So it's just so easy to do. And that gives you right off the top. In fact, most of the time you just write it out and you can fill in the numbers. And you're done. Okay. Now, I've just shown you all this. They're going to show it to you too. So let me erase. Well, let's see. No, I don't need to. A convenient way to calculate U cross V, which we already did, is to use the determinant form with cofactor expansion shown below. I didn't want to give those terms. I remember now, this guy also writes linear algebra, so he's going to use the same terminology. So U cross V To do that, of course, always put your I, J, K vectors, unit vectors on the top. Then the first one here, U1, U2, U3, second one, V1, V2, V3. Components under there. And then for this component, this value of your I component there, you wipe out the first row, first column, first row, and then do the determinant of the matrix that's left. And that's U2, V3, and then they do minus U3, V2. It's fine, times the vector I. Okay? And because, and what they're calling a cofactor expansion, that's the sign change. That's the plus minus plus minus plus. So you do a minus, wipe out you always have the first row wiped out, wipe out the second column now, and then do U1, V3 minus U2, 3, V1. Okay? And then go to the third one, that's a plus, that's the cofactor type thing. So you wipe out the third column, always keep the first row wiped out. And this is U1, V2 minus U2, V1. Okay. So that's how we did it the first time, and that's exactly what we got before. They always do the U's before the V's, which is fine. It doesn't really matter. It's multiplication of numbers, and that's commutative. It doesn't matter. Okay? Note that the minus sign in front of the J component, each of the three 2x2 determinants can be evaluated using the diagonal pattern. The down diagonal is positive, the product of the down diagonal is positive, the product of the up diagonal you negate. Okay, so it's always AD minus BC. Now, so let's just do for funsies. What would be the determinant of that? Start with the down diagonal. 2 times minus 1 is? -2. And you use the positive value of that, which is -2. Okay, you don't change the sign. But then the up one, you... Yeah, negative what?
12.
12, yes. And -2 minus 12 is -14. There it is, right? This one would be what? 12, you got it, because 0 times anything is 0. Yeah. Good. Now that leads to something else. If you're doing determinants of a matrix, however big or what anything it is, find the row or the column with the most zeros in it, and that makes it go much, much faster.
Right, it's a lot easier.
Because a lot easier. But we're not worried about that. We're only using 3x3s, and they're pretty easy. Okay, so let's do these two. For U equal I minus 2J plus K, V's equal to 3I plus J minus 2K, find the following, U cross V. How would you do that?
U times V is 1. What's that? I, J, and K?
Yeah, put I, J, K at the top. Now, do you like to do the cofactor like we did at the second, or stretching it out like I showed you before? I don't care.
We do the cofactor.
Okay, let's do it that way then. We'll end this then. What do I put on the second row?
You have
1.
-2.
-2. What did you say? 1. Yeah, okay. 1, okay. Third row? 3. 1. -2. Okay? And what does this give you? The I component. You wipe out first row, first column. I set them backwards. Okay. Say again?
-2.
How did you get that?
Oh, no, sorry. It'll be 4.
4.
4 and 1. 4.
Say again?
4.
This one is 4 minus that one. 4 minus 1.
Oh, 3.
Yes, 4 minus 1 is 3, and that would be your I component. Okay. Now, what I'm going to do is wipe out that and those. Okay. Which one you don't want to do next? J. Okay, and probably let me wipe out this one too, just so don't need the circle anymore. All right. Now we're going to do J. So what else do we wipe out? The row 2. I mean column 2. Okay. Okay. Now, what do we have to remember about the J?
Aren't you doing the outside one? So
Yeah, we're going across here. S-I-G-N. Sign. Oh, that's negative. So that's going to be a negative. Now we do. Yeah, but with a minus sign, so it's minus 2. Yeah, but because it's up diagonal, it's negative. Minus 3. Minus 2 minus 3 is? Minus 5. J. Okay? And, okay, now let's wipe those out so it doesn't get too crowded and ugly and miserable. Okay? And now we're going to do our K component. And first we determine the sign, and that's a plus. And we'll wipe out the third column now, and that will be 1. Yeah, but it's up diagonal, so that's, yeah, 1 plus 6 is 7K. So that should give us 3I plus 5J plus 7K. All right, that's our guess. Let's see what they give. You got that down pretty well? Okay, let's see what they do. They set up the vector, their determinant just like we did. IJK, 1, negative 2, 1, 3. Oh my goodness, 1, negative 2. And I drank a Coke, in between classes, and I'm still so out of it. I don't have my energy strength back yet. Okay, let's see what they did. They didn't show you how they did it. Wiping out the first row and first column to determine what's left, so they wrote that here. And if you like doing this, do it. That might make it clearer for you. But I think if you just do this, you see that same determinant right there. So that's times the I. You do the same with the J, except that's a negative position, so you be sure to do that. Wipe out this row and this column. You have 1, 1, 3, negative 2 here. So that's the determinant here times J. And then for the K, wipe out first row, third column. And what you have left is 1, negative 2, 3, 1. Then they do 4 minus 1, 3I. Let's see how many steps they take. Yeah, 4 minus 1 times I. Minus out front, negative 2 minus 3J. Plus out front, 1 plus a 6K. And that gives you 3I plus 5J plus 7K. Right? Okay. Now, do the B one and see what we get. What's going to happen if you do V cross U? You tell me what to write.
3.
Not yet.
Well,
I, J, K. Got that.
now we start with
3,
1,
1, negative 2, 1, negative 2, 1. Okay. What's next?
Starting with the first one.
Second.
Once you start with 3, wiping up.
Second.
Once you wipe out, well, start with the 3 and go down. Start with the
I. Okay, I like that. We'll start with the I. And you wipe out vertically and horizontally. That's what I thought I heard you say. Right, okay. And so what goes in front of that? 1.
And then 4.
Second.
1 and 4.
Okay, but what sign is this?
Negative.
Negative. 1 minus 4 is?
3.
1 minus 4 is?
1 minus 4.
Yeah.
Negative.
Negative 3. Negative 3i. Okay, got that one. So let me take out what we don't need any. Oh, I didn't mean that. Okay. That first row is always done. Now we're going to do the J. Before we do it, it's negative. And then wipe out that column. And what do we have? 3. That's a positive. 3 plus 2 is? 5. J. Okay. Now let's wipe out. Let's just wipe out. Okay, okay, okay. 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 And what sign is that? Positive. And what we do here? Negative 6. It's going up. Negative 1. Okay. Yeah. So minus 6 minus 1 is? Negative 7k. So that answer is minus 3i minus 5j minus 7k. Guess what? Exactly the opposite of the other. The other was 3i plus 5j plus 7k. So this is going in exactly the opposite direction. Along the same line, but exactly the opposite direction. Exactly. And that's what I said before. U and V name a plane, and one normal is this way, the other normal is that way. Exactly the opposite of each other. Okay? Now, here's the other thing to note here. Okay? You tell me, just pick a direction for you. Straight up. Okay, that's fine. And how about V? Okay. That's not going to work well because it's a collinear. And when you do that, you're going to get 0. Do me something that you can do. How about, okay, you'll be up here and V will be over here. They're not perpendicular to each other. U cross V is going to be this one. U cross V, this one. But if we do V cross U with right hand, V cross U is that way. Exactly the opposite of each other. That's why one's positive, one's negative. Now we're going to do almost what you said. Let's do V cross V. Okay. I could have left. Could have been a lot smaller. I could have left. I keep thinking of things I could have done to make it easier. Okay. V cross V. I left my IJK there. Finally, I left something right. And what goes here? 3. 1 and negative 2. I remember the. Okay. And what goes in the bottom? 3. 1. Same thing. Okay. So let's go to it. And we'll choose I first. Wipe out first row, first column. Okay? And what do you have here? Do you like to do the determinant, or you want to go and figure out what the determinant is? What's that?
We can do the determinant.
You mean write it in?
Write it in.
Or just calculate it? Which one you mean? I don't care.
We can go ahead and write it in. Like,
Just write it in. And okay, like this. Put a 1, -2, 1, -2. And do your I there. That's fine. And then for the J, we would wipe out that and that. And what would be your determinant there? So I'm just doing it a couple different ways so you can choose what. But what do we always put first before J? Minus sign. And then what determinant do we have?
We have
3.
-2.
Second? And 3, -2, yeah. And then that's times J. And then, oh, I'm erasing, you tell me what I'm going to write. Plus, because of the sign, determinant of
Yeah,
3, 3, 1, K. Okay, sorry I didn't plan well. All right, let's do that determinant. What do we get?
-2.
-2.
-4.
Up diagonal is?
Oh,
Okay, so -2 plus 2, 0I, minus
-6.
up diagonal, sir? They're the opposite of what it was. It was a -6, which is +6. It'd be -6 plus 6J, right? Okay, plus 3 minus 3K. So that's 0I minus 0J. Who cares what sign 0 has? Plus 0K. Guess what? It's a 0 vector. There is no component to it. Okay? So a cross of any vector that is collinear with any other vector, whichever direction it's going, is going to produce a 0 vector. No, there is no orthogonal vector that will do that. So, interesting. Now, let's go back to our dot product. When you do a dot product to two vectors that are collinear, you basically have the largest product you can get out of that, either largest positive or negative. Okay? When you do a dot product to two vectors that are anything else, the number gets smaller, either positive or negative. You're getting closer to 0. But when they get perpendicular to each other, your dot product goes to 0. But on cross products, when they're perpendicular to each other, you get the maximum length vector normal, and then the closer they get to being collinear, that decreases or increases, it goes to 0. So a perpendicular dot product is going to be 0. A parallel dot product is going to be maximum value. A perpendicular cross product is going to be maximum value, either positive or negative. And when the 0 difference between them, in other words, they're going in the same direction, it goes down to 0. Okay. Now, by the way, sorry, my throat's hurting. Okay, we did those. Oh, yuck, I forgot. We did B, but I forgot to let you see what they do for B. Okay, U cross V, IJK, 3, 1, negative 2, 1, negative 2, 1. Set it up, and this is how we didn't do it on this one, we did it on the other one. 1, negative 2, negative 2, 1, I, determinant of that I, minus the determinant of 3, negative 2, 1, 1, j, plus the determinant of 3, 1, my throat hurts, 1, negative 2, k. And then when you did that, that's 1 minus 4, I, minus a 3 plus 2j, plus, plus a negative 6 minus 1k. When you add those together, or subtract them, whatever, negative 3i minus 5j minus 7k, which is exactly the negative of u cross v. Exactly, precisely, identically the negative of that. Okay? When you do v cross v, you use 3, 1, negative 2, 3, 1, negative 2. Hey, they didn't show you anything. They just said, that's a zero vector. Okay? A cross product of any two parallel vectors is zero vector. Remember, it's got to be a vector, so it's a zero vector. That's why they bolded the zero. I can't bold the zero, so I have to put a vector sign over it. I am so sorry, but I'm running out of juice. All right. Here is theorem 11.7. I didn't drink a whole Coke, but I just thought I'd need a little bit. I think I needed a couple of them. Okay. Algebraic properties of the cross product. If u, v, and w are vectors in space, meaning three-dimensional vectors, c is any scalar, any real number in the world. Now, we've already run into this before, but we didn't state it. U cross v is exactly the opposite of v cross u. So it's exactly the negative thing. We showed that last time. U cross v was 3i plus 5j plus 7k, and v cross u was negative 3i minus 5j minus 7k. Exactly the opposite. Now this is one we didn't show, but let's see if it seems to make sense. When you cross u with the sum of v and w, okay, now v and w, remember, are vectors in space, meaning both three-dimensional vectors. So you can add two three-dimensional vectors. If one is two-dimensional and one three, you can't add those. But if they're both three-dimensional, you can add them. And that gives you a vector. The sum of two vectors is a vector. And here's the surprising thing, or maybe not be surprising. It's the same as u cross v plus u cross w. So it's a distributive property of vector addition over, or vector multiplication over vector addition. All right. Now here's another one. If you do some scalar times the product of u cross v, that's the same you get if you have that scalar times u cross v, or u cross the scalar c times v. That looks like a little bit of a distributive property of a scalar multiplication over a vector. But, yeah, well, not distributive. I don't know what. Yeah, this is sort of a distributive property, but it's usually distributive with plus signs with a cross product, but it still works. But notice this: that doesn't multiply by both of them; it only multiplies by one. So most of the time we handle this going the other way. If you have a constant times, if you have a vector that has a constant factor in it, pull the constant on the outside and just multiply the two vectors together. The smaller you can keep those numbers, the better. Okay? So if you can pull out common factors, take it out. Now, if this one had another common factor like k, kb, then pull out c times k. Okay, pull them both out and then use. All right. Well, this is sort of a dumb one, but it's okay. It's dumb. The zero vector to me is sort of dumb anyway. It's not really a vector, but you have to have it there. Has no magnitude and no direction, so but we still call it a vector. So u cross 0, you can do this out in your matrices, in your determinants and stuff, and you'll see it's true, is the same as u cross v, not the negative of it, but the reason it's the same and not negative is it's always 0. So 0 and negative 0 is the same. So that's a vector 0. Remember, cross product always produces that. But, and we just saw it earlier, u cross u or v cross v, w cross w, always a 0 vector. Okay? Vector and any vector that's collinear with that, either positive or negative collinear with it, longer, shorter, whatever, but collinear with it, don't produce a 0 vector. And then, here's a mixture of dot and scalar product. Remember when you cross product here, I said scalar, cross product here, that's going to produce what kind of an answer? Okay. What kind of an answer? Scalar or vector?
Cross product?
Yeah.
Scalar.
No, cross product always produces a vector. Okay, we don't see that here, but it is true. Okay, or here we did. This is 0 vector. Okay, so this produces a vector, and you can dot a vector with a vector. That's going to give you a scalar. Okay. Now here's sort of the weird thing. U dotted with v cross w is the same as u cross v dotted with w. What? Doesn't seem to be any logical sense of why that's true. But it's true that this produces a vector, dotted with a vector gives you a scalar, and that's a scalar. That part makes sense, but why would it be otherwise? Okay? It's just a rule. So it is true, it's a theorem, it says these are true. These are properties. So I'm not sure you use that one very much. I bet you will use it a lot now, so I say that, but that is a true. The others make perfect sense when you think about it. Pretty much. Okay. Now here's another theorem. Now you have a little proof there, and I'll let you look at the proof. I don't think they prove all the pieces, just one piece. Where is, I'm sorry. I flipped the page too soon. Okay. This one was at the bottom of page 780. This one's at the top of 781. Okay? Here's geometric. The difference is these were algebraic properties of the cross product. Here are geometric properties of the cross product. Okay. Oh, goodness. Yeah, we're almost out of time, aren't we?
Yes.
Okay. I think we can get this covered. Whew. Let U and V be non-zero vectors in space. Let theta be an angle between U and V. So here we have two vectors, U and V. Right now the angle between them is an acute angle. Here's two others. Yeah, probably close to being acute. Okay. Here are two others. Yeah, that's obtuse, but they're not in the same direction. Okay. So any two angles in space, two vectors in space, they can't be the zero vector, and they have some angle theta in between them, U and V. Now, U cross V is always, and we already talked about that, orthogonal with both U and V. Both of there. Close like this, wide like this, whatever, you always don't get a vector that's perpendicular to both. Now, here's another one. This is sort of interesting. The magnitude of U cross V is the magnitude of U times the magnitude of V times the sine of that angle in between them. Okay? Now let's think about sine for a minute. In an acute angle, the sine is always positive. So cosine, so it's tangent, so it's okay. An obtuse angle greater than 90, the sine of that is also positive. But remember back with dot product, it's A times B, magnitude of A times magnitude of B times the cosine of A over square. When you had an obtuse angle, the cosine was negative. Not so here. Magnitude of U times magnitude of V times the sine of V. Now, if you get this angle beyond 180 degrees, now the sine of that is negative, as is the angle all the way around there. So that would be. All right. U cross V is 0 if and only if U and V are scalar multiples of each other. In other words, they're collinear. We talked about that before. Whereas U dot V is 0 if and only if U and V are perpendicular to each other. Okay? So these are parallel, dot product perpendicular. Okay? Now, magnitude of U cross V is the area of a parallelogram having U and V as the adjacent sides, whichever they are. Area of that parallelogram. That's an interesting geometric property. Goodness gracious. All right. How are we doing? A minute or two more?
About three.
About three, okay. There is a proof there for that fourth one, the parallelogram thing. Let's see if they go over that. Yeah, here they do. No, not quite. But U cross V and V cross U are perpendicular to the plane determined by U and V. We already talked about that. One way to remember the orientation of the vectors U, V, and U cross V is compare them with the unit vectors I, J, and K. This is rather, yes ma'am.
You busy?
I'm in class.
Oh, okay,
Yeah.
I'll wait.
Yeah. I get out of class in just a few minutes.
Okay.
Never ceases to amaze me. Okay. I don't know if this is helpful to you or not. It's definitely true. Orientations of the vectors U, V, and U cross V is compare them with the vectors, unit vectors I, J, and K, remembering this. I don't like the way they wrote that. Vector I, X direction, vector J is in the Y direction, and K is in the positive Z direction. So if I were writing this, I would do it this way. I cross J equal K. Okay? All right? Now, that at least is the directions are right. Guess what? The magnitudes are right too. Because from the last thing we said, magnitude of this times magnitude of that, well, that's 1 times 1, so yeah, that's going to be 1. It's going to be a unit vector. Okay? Now, then U cross V is going to be just like I cross U. It's going to be positive upward, you would say. U cross V would be that. The three vectors U, V, and U cross V form a right. Okay. And so why don't they just talk about the right-handed system? We've already done that. Whereas the three vectors U, V, and U, V cross U form, I don't call it a left-handed system. It does. It just points down. Okay. So why change the hands? I don't think so. Okay. Now the reason I prefer to write it that way is this. I want you to notice that. This is also true. J cross K is equal to I. And K cross I is equal to J. That's what I thought they were going to get at here. That's why I like to write them this way. Not that way, but this way. So you have IJK, IJK, IJK. They're always in that order. When you start reversing them, then that makes a minus, a minus, a minus. So I thought that's what they were going to get at, but they didn't. That's why I wanted to correct them and write it that way. Okay, is that run us out of time?
Yes.
Sorry. Okay, we'll start next time with example 2. I can't believe we only got, well, that we did the other stuff too. So we'll start with example 2 next time. Okay. What's that?
Oh, you saying cool.
All right, good deal.
Wednesday, right?
Today's Wednesday.
Monday?
Monday. It'll be Monday.